Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired, and refreshed. Now, if you find my videos interesting and important to your studies, also please don't forget to subscribe. So here's another problem in Vitamath. Two externally tangent circles of radii 12 centimeters and 16 centimeters are internally tangent to a third circle of radius 36 cm. Determine the area of the smaller region that is outside the smaller circles but inside the biggest circle. So to help analyze the situation, let's have the figure, this problem. So these are the two externally tangent circles, and they are internally tangent to a third circle of bigger radius 36 as shown. And we are required to find the area of the smaller region that is outside these smaller circles but inside the biggest circle. So we are referring to this area here. So to help analyze the situation, that's having located the centers of the two small circle, let's have the center of the biggest circle, which is 36 cm in radius, and let's connect the centers with the triangle so that we can analyze the situation. So therefore, the side here is 36 because if you extend this, that's the radius of the 36 cm radius circle minus 12, so this is 24, and this is 12 plus 16, so 28, the sum of the radii of the smaller circles, 24. Then this is 36 from here up to the point of tangency 36 minus 16, so this is 20. So to continue, take note that this triangle is possible because the sum of the shorter sides 20 and 24 is greater than the longest side of the triangle 28. So always evaluate the triangle if it is possible. The problem might be wrong. So let's extend the these sides. So that's 12. This is the center of the biggest circle. Call that point B. That's 16. Then call that C. Call this theta 1, theta alpha 2, alpha 3, theta 2, theta 3. And this is area S. So we are required for that. Then to set up the equation of area S, it is equal to the area of this sector. I hope you can visualize it. Then minus the area of this triangle. Then minus the area of this sector 2. Then minus the area of this sector 3, leaving this required area. So again, area S is area of this sector of radius 36 minus area of this triangle minus area of this sector and minus area of this sector. Now to solve for the area of the triangle, we need this angle theta 1 and of course alpha 2 and alpha 3 to determine theta 2 and theta 3 for the area of these two sectors. So alpha 1, for theta 1 we apply cosine law to solve for theta 1. Then theta 1 is the biggest angle among these interior angles of the triangle. So if theta 1 is an acute angle, then definitely alpha 2 and alpha 3 will also be acute. Then because this is the biggest angle for this interior angle, it is crucial to apply law of sines after we solve for theta 1, especially if theta 1 is very small angle, but that's not very small. That is the biggest angle, or the biggest angle because it is opposite the longest side. So that's the technique. You have to solve for theta 1 first to solve for the biggest angle. So by cosine law, opposite side square equals sum of squares of the other sides minus twice the product of the other sides times cosine of the angle included between these two sides. So area S is area of sector 1, which is the area of this entire sector. Call that area S2, area S3, and this one is area S1, this sector here, minus area of triangle, this triangle here, minus area of S2, minus area of S sub 3. So to solve for area S1, we need theta 1. So by cosine law, 28 square equals 24 square plus 20 square minus 2 times 24 times 20 cosine of theta 1. So using your calculator there, theta 1 equals 78.46 degrees. Then we convert that to radians to compute area S1 as for sector, because it should be in radians in the formula 1/2 radius square central angle. So 78.46 degrees times pi over 180 equals 180 degrees equals 1.3694 radians. Then we apply the law of sines to solve for alpha 2 and alpha 3. So we are sure that alpha 2 and alpha 3 are also acute angles, in fact less than 78.46. So 20 as to sine alpha 2 equals 24 sine alpha 3 equals 28 as to sine of theta 1, which is 78.46 degrees. So solving for alpha 2, 20 sine 78.46 over 28, then inverse sine alpha 2 is equal to 44.41 degrees. Then 24 sine 78.46 over 28 inverse sine alpha 3 is equal to 57.12 degrees. So theta 2, 180 degrees minus alpha 2. Then let's convert that to radians. Theta 2 is equal to 135.59 degrees times pi over 180 degrees. So theta 2 is equal to 2.3665 radians. Alpha 3 is 180 degrees. Theta 3 is 180 degrees minus alpha 3. So it is equal to 122.88 degrees times pi over 180 degrees. So theta 3 is equal to 2.1447 radians. So we can now compute area S. Area S is area S1, 1/2 36 square central angle theta 1 in radians 1.3694. So 1/2 36 square times 1.3694 minus area of triangle, which is 1/2 product of adjacent sides 1/2 2420 times sine of the included angle. So 1/2 24 times 20 sine of theta 1, which is 78.46 degrees. Then minus area S2, which is 1/2 12 square. Theta 2 in radians 2.3665. And finally minus 1/2 area S3 1/2 16 square times theta 3 in radians 2.1447. So area S is equal to, the first term is 887.37, second negative 235.15, third negative 170.39, and this is negative 274.52. So area S can now be calculated. It is equal to 207.3 centimeters square. Now for your part, I want you to compute this bigger region. So this is your problem. Determine the area of the bigger region, this one, and I want you to show that the answer is equal to 2607.6 centimeters square. So that's all for this video. I hope that you learn another thing in mathematics, which is very important in your journey as civil engineering as engineering students of any field, and I hope that it can develop your thinking skills.